In this lecture, we're going to give the definitions for the general trigonometric functions that apply to all angles. Our goal is to extend the right triangle definitions that we've already learned to all angles. As a reminder, when we have a right triangle, there are 6 different ratios that we can form from the 3 sides of this triangle. And the 3 primary ratios are given by the sine, cosine, and tangent functions. The ratios of any 2 sides of this triangle are dependent on this angle, and we use that correspondence between the ratios and the angles to solve right triangles for missing sides and missing angles. Now we want to find a meaningful way to define these ratios for angles that are not part of a right triangle and possibly not part of any triangle at all. So we'll start by looking at this angle not as part of a triangle, but is formed by 2 rays, both extending from the vertex of the angle. Now these 3 segments no longer need to be thought of as the sides of a right triangle. They can be thought of as components whose ratios correspond to the direction of one side of the angle relative to the other, similar to the rise over the run for the slope of a line. We need to give new names or labels to these components when we define these ratios more generally, but we also need to see what happens to these components when we look at angles that are not between 0 and 90 degrees. Let's rotate this side of the angle until we have an angle that's greater than 90 degrees, and look at what happens to these 2 perpendicular segments. Now, to form those perpendicular segments, we need to extend one side of the angle in the opposite direction, which means that for some angles, one or more of these components will have to be negative. There's a convenient way to define these components that will naturally account for whether they're positive or negative, and will give us new labels to use in our general definitions. Imagine we place this angle in a rectangular coordinate system so that one side of the angle is on the x-axis and the vertex is at the origin. Then these 2 perpendicular components can be thought of as horizontal and vertical components, and they correspond to the x and the y coordinates for a point on this side of the angle. We'll use this idea to define a standard position for angles, and then we can give the definitions for the general trigonometric functions. In standard position, our angles will be placed in a rectangular coordinate system with the vertex at the origin. We can think of a ray starting on the positive x-axis. That'll be the initial side of the angle, and that ray will be rotated through an angle, giving us the terminal side. This rotation will be in the counterclockwise direction, so that we go first into quadrant 1, where the x and y coordinates are both positive. To get the components used in the trigonometric ratios for this angle, notice that any point along the terminal side will determine a horizontal component and a vertical component equal to the x and y coordinates for that point. The third component will be the distance between the origin and this point on the terminal side, which we'll call r. And r squared will always equal x squared plus y squared, satisfying the Pythagorean theorem. X and y can be positive or negative, depending on what quadrant the terminal side is in. But r will always be positive. That's the distance between the origin and the point on the terminal side. We're now ready to give the definitions for our general trigonometric functions. Here's our angle in standard position. It's helpful to think of this angle in quadrant 1 when you're first learning these definitions, so you can see this right triangle and you can apply the right triangle definitions to this diagram. Here's a reminder of the right triangle definitions. Sine is opposite over hypotenuse. In this diagram, the opposite leg is y and the hypotenuse is r. So sine of theta is y over r. Cosine is adjacent over hypotenuse. In this diagram, the adjacent leg is x, so cosine of theta is x over r. And tangent is opposite over adjacent. Tangent of theta is y over x. We also have our reciprocal functions. Cosecant is the reciprocal of sine, so cosecant is the ratio of r over y. Secant is the reciprocal of cosine, so secant of theta is r over x. And cotangent is the reciprocal of tangent. Cotangent of theta is x over y. And that completes the 6 definitions for our general trigonometric functions. We can see that for acute angles, such as the one in this diagram, The general definitions are the same as the right triangle definitions, but the general definitions can be applied to any angle. And now we'll look at how these ratios correspond to the direction of the terminal side of an angle. Notice that for an angle that terminates in quadrant 1, we have a positive horizontal component because it's in the direction of the initial side of the angle, or to the right. And it has a positive vertical component because it's going up from the initial side. Let's compare this to an angle that terminates in quadrant 2. We choose any point along the terminal side to form our segments. This angle has a negative horizontal component because it's going in the opposite direction of the initial side, or to the left. And it has a positive vertical component because it's going up from the initial side. Notice that these components are just the x and y coordinates of this ordered pair. Now let's look at an angle in quadrant 3. We pick a point on the terminal side to form our segments. And this angle has a negative horizontal component and a negative vertical component because it's going down from the initial side. And an angle that terminates in quadrant 4 will have a positive horizontal component because it's in the direction of the initial side, and a negative vertical component because it's going down from the initial side. And remember that the r in these ratios is always positive. We can consider that the radial component of this angle, and its orientation is always in the direction of the terminal side of the angle. So the angle determines the direction of the terminal side, and that direction determines the value of these ratios and whether they're positive or negative. The trigonometric functions pair up the angles with their corresponding ratios. There are lots of applications for this. For example, imagine any point in the plane. The position of the point is given by the x-coordinate and the y-coordinate. The distance between the point and the origin is the magnitude of the point, which we call r, and that segment also defines a direction relative to the positive x-axis, which we label with the angle theta. This gives us two ways of representing the location of a point in the plane: the familiar rectangular coordinates x and y, and the trigonometric or polar coordinates r and theta. The trigonometric functions, along with the Pythagorean theorem, allow us to convert between the x and y and the r and theta. Later in this course, we'll see that those conversions are very important for complex numbers, and we'll use them for two-dimensional vectors to convert between the horizontal and vertical components of a vector, and the magnitude of the vector and the direction given by the angle. We'll also use these when we look at points on a circle, and we relate the x and the y coordinates of that point with the radius of the circle and the direction associated with that point.